From the moment you wake up, to the systems that fly our planes, to the medical gear that literally keeps people alive, our entire world is running on software. But have you ever really stopped and thought about how it all gets made? It's definitely not magic, and it's so much more than just a single programmer hacking away at a keyboard.
So think about this for a second. On one side, you've got a life-saving insulin pump. I mean, one tiny little bug in its code could be catastrophic. And on the other side, an app you use to buy a new pair of sneakers. They feel like they're from completely different universes, right? But believe it or not, they share this fundamental, kind of hidden connection.
And that's it, right there. Software engineering. This is the disciplined, structured, methodical way we approach building the software that powers, well, everything. It's the huge difference between a little hobby project and a reliable, rock-solid system that people can actually depend on. To really get why this discipline is so incredibly important, let's circle back to that medical device. We're not talking about a simple inconvenience if something goes wrong here. We're talking about systems where the stakes are quite literally life and death. Yeah, and when you see it laid out like this, the stakes become crystal clear. An insulin pump has to be basically perfect. It's constantly monitoring blood sugar, doing calculations, and delivering a super precise dose of insulin. If that software messes up at any point, if that calculation is even slightly off or a dose is missed, the consequence isn't a 1-star review. It's a coma or even death. You just can't wing it when lives are on the line. You need engineering.
Okay, so we've seen why it's so critical. We get it. But what is software engineering really? What's the secret sauce that separates a safe medical device from a dangerous one?
The key phrase here, the one I really want you to grab onto, is all aspects. See, software engineering is not just the act of programming or writing code. It's a full-blown engineering discipline that covers the entire process, from the very first spark of an idea all the way through to supporting and maintaining that software years after it's been released. It's the whole shebang. Now, this is a really common point of confusion, so let's just clear it up. Think of it like this. Computer science is like discovering the laws of physics. It's the deep theory and fundamentals. Software engineering, on the other hand, is like being the civil engineer who actually uses those laws of physics to build a safe, reliable bridge that won't fall down. It's all about the practical application. And those practicalities, they have very real costs. Just look at this breakdown. For your typical professional software project, a crazy 40% of the cost isn't even for writing the code. It's for testing and validating it. And why is that? Well, because finding and fixing a bug before it gets out into the real world is so much cheaper and safer than trying to clean up the mess after it fails. Okay, so if we're spending all this time, effort, and money to properly engineer software, what are we actually trying to achieve? What are the core ingredients of a genuinely good piece of software? Well, it all starts with a process, a sort of roadmap. First up is specification, figuring out exactly what the software needs to do. Then comes development. That's the design and coding. Next, and this is huge, is validation. Testing, and more testing to make sure it actually works. And you're still not done. Finally, there's evolution, because software has to change and adapt to new needs over time. And that last step, evolution, leads us straight into our first essential quality, maintainability. Great software is never really finished. Just think about your phone's apps. They're always getting updates, right? New features, security fixes. Good software has to be built from the very beginning with the idea that it's going to change. Next, and this takes us right back to our insulin pump example, is dependability and security. You have to be able to trust it, period. This is the promise that the software won't break in a way that causes physical harm or costs you money, and that it's built to be safe from hackers and other bad actors. Then we have efficiency. Come on, we've all used that one app that just sucks your phone's battery dry in an hour, or makes your computer's fan sound like a jet engine. Good software is respectful. It does its job without being a resource hog. And finally, there's acceptability. This is the human element, and it is so important. A piece of software can be the most technically brilliant thing ever created, but if people can't figure out how to use it, or it's just plain annoying,
it's a failure. It has to be designed for the actual people who are going to be using it.
Now, building software that has all these amazing qualities isn't just a technical puzzle. Given how much power software has in our world, it also comes with some really profound ethical responsibilities.
You know, at the very core of this whole thing is a simple truth, and it's captured perfectly in the professional code of ethics. It says that software engineers have significant opportunities to do good or cause harm. The decisions they make really matter. So, to help guide those big decisions, professional groups have a code of conduct. The main idea is that an engineer's duty goes way beyond just their boss or their company. They have to put the public's interest first, make sure their products are top-notch, and always maintain their professional integrity. It's a real commitment.
All right, let's zoom out one last time. We've talked about the what and the why of software engineering. But now, let's just take a moment to appreciate the massive scale of it all and the challenges that are still ahead.
Just let that sink in for a minute. This isn't some niche little industry we're talking about. The economies of all developed nations are now fundamentally, completely dependent on software. It is the invisible backbone holding up our entire modern world. And this field never stands still. The engineers of today are tackling these huge, complex challenges, like how do you get software to work perfectly across thousands of different devices? How do you keep up with lightning-fast changes in the world? And maybe the biggest one of all, how do you build systems that we can all genuinely trust? So the next time you open an app or install an update, or just trust a system to do its job, maybe pause for a second and ask yourself, was this thing just coded? Or was it engineered? Because now you can see the difference. That hidden, disciplined, and absolutely essential work that keeps our world spinning.